Right now, at this very moment, a spacecraft is drifting through one of the most misunderstood regions in the entire solar system. It has been traveling for decades. It is moving at roughly 58,000 kilometers per hour, fast enough to cross the continental United States in about 3 minutes. And it is still surrounded by more unknown objects than known ones. But here is what most people get wrong about the Kuiper Belt. The danger was never the thing we imagined. It was never the crowded ring of colliding ice and rock from the diagrams. The real danger is quieter than that, older than that. If you enjoy drifting through the deeper questions of space and science, do consider subscribing to Blackout Universe. It genuinely helps. Make yourself comfortable. Let's begin. For most of human history, the solar system had a neat and comfortable edge. There was the sun at the center, the planets arranged in their familiar sequence outward, and then, beyond the last of them, a kind of ending. A boundary where the solar system simply stopped and empty interstellar space began. We drew it that way on charts. We taught it that way in classrooms. The solar system was a finite, mappable thing, and its outermost border was wherever we decided Pluto was. That picture was wrong, not slightly wrong. Not wrong in the way that most scientific models are wrong at the margins, where the core idea holds and only the details require adjustment. It was wrong in the way that matters most. It was missing an entire region, a vast, cold, dimly lit wilderness stretching billions of kilometers beyond Neptune, populated by hundreds of thousands of objects, possibly billions of smaller ones, and governed by gravitational forces that took decades of observation to even begin to understand. We call it the Kuiper Belt. And the story of how we came to know it is, in many ways, the story of how difficult it is to see something that does not want to be seen. The idea that something might exist beyond Neptune is older than most people realize. In 1943, a researcher named Kenneth Edgeworth published a paper suggesting that the outer solar system might contain a vast reservoir of small icy bodies, material left over from the formation of the planets, never gathered into anything large enough to be called a world. His reasoning was straightforward. The solar nebula, the disk of gas and dust from which the solar system condensed, did not simply end at Neptune. It extended outward, and in the cold, sparse outer regions, where objects were too widely spaced to accumulate into planets, the material would have remained small, scattered, slow. A population of frozen remnants drifting in the dark. Almost no one read Edgeworth's paper. It was published in an obscure Irish journal during a period when the world had other things on its mind, and it passed without significant attention. 8 years later, in 1951, a Dutch-American astronomer named Gerard Kuiper published a similar idea, that a disk of small icy bodies might have existed in the outer solar system in the early history of the planets. Kuiper's reasoning was slightly different, and he actually concluded that this disk had probably been dispersed by Pluto's gravity over time and might no longer exist in significant form. He was wrong about that conclusion, but his name attached itself to the region anyway. Edgeworth's name is carried by it in some communities. Some astronomers call it the Edgeworth-Kuiper Belt, in acknowledgement of the earlier work, but most of the world knows it simply as the Kuiper Belt. For decades after these papers, the idea remained theoretical. Astronomers suspected something was out there, the mathematics of short-period comets. Comets with orbital periods of less than 200 years, the kind that returned to the inner solar system on human timescales, suggested they had to come from somewhere relatively nearby. The Oort cloud, the vast spherical shell of comets at the outermost edge of the solar system, was a known reservoir for long-period comets. But short-period comets followed orbits too flat, too aligned with the plane of the solar system, to have originated from the Oort cloud's random spherical distribution. Something else was feeding them into the inner solar system. Something in the plane, something closer. The confirmation came in 1992. Two astronomers, David Jewett and Jane Liu, had spent years scanning the outer solar system with telescopes, looking for the faint, slow-moving signatures of trans-Neptunian objects, bodies orbiting beyond Neptune. It was painstaking work. The objects they were looking for were dark, cold, and billions of kilometers away. They reflected almost no sunlight. They moved slowly against the background of stars. Finding them required patience, careful comparison of images taken nights apart, and a willingness to accept that the search might go on for years without result. On the night of August 30th, 1992, they found one. A small, reddish object orbiting the Sun at a distance of roughly 44 astronomical units, 44 times the distance between the Earth and the Sun. They designated it 1992 QB1. It was not much to look at. A faint point of light, barely distinguishable from the stars behind it, moving almost imperceptibly across the sky. But it was real, it was there, and it was exactly where the theory had predicted something should be. Within a few years, dozens more were found. Then, hundreds. Today, the catalog of known trans-Neptunian objects runs into the thousands. And orbital models suggest the true population of the belt is orders of magnitude larger than what we have managed to detect. The region that Edgeworth imagined in 1943, that Kuiper theorized in 1951, that Jewett and Liu confirmed in 1992, is real, and it is enormous. We gave it a name. We drew it on updated diagrams of the solar system. We added it to textbooks and educational videos, depicted as a broad, diffuse ring of icy debris beyond Neptune, visually similar to the asteroid belt between Mars and Jupiter, but larger and colder. And in doing so, we made the same mistake we had made before. We made it feel known. We made it feel mapped and understood and safely placed within a diagram. Then we sent a spacecraft through it. The New Horizons mission launched in January 2006, designed to make the first close flyby of Pluto and then continue outward into the Kuiper Belt. It traveled for 9.5 years before reaching Pluto in July 2015, sending back images and data that immediately overturned nearly everything planetary scientists had assumed about the outer solar system. Pluto was not the simple, dead, frozen world the models predicted. It was geologically active. It had mountains and plains, and an atmosphere that expanded and contracted with the seasons of its 248-year orbit. It had color and structure and complexity that no one had expected. And then New Horizons kept going. It crossed into the Kuiper Belt proper, continuing its slow arc outward through that vast region of icy debris. It flew through the heart of the belt. It passed within range of objects that had never been seen up close before. And it sent back data that scientists are still working through today, data that continues to suggest that the belt is stranger, more complex, and more dynamic than the diagrams ever suggested. The comfortable picture had gaps in it, large ones. The belt we had named and drawn and theorized about turned out to be something considerably more difficult to understand than a simple ring of leftover ice. What we thought we knew was an outline, a rough sketch made from enormous distance, with instruments not quite sensitive enough to see the details, filtered through models that made assumptions we didn't know we were making. The details, it turns out, are where the danger lives. And the danger of the Kuiper Belt is not the danger most people imagine when they hear the word. It is not the collision of dramatic, city-sized boulders. It is not the sudden catastrophic impact that Hollywood has made familiar. It is something quieter, older, and in many ways more absolute than that. To understand what the Kuiper Belt actually is, not the diagram version, but the real one, we have to begin with its structure, with its true dimensions, with the shape of the thing as it actually exists in space, rather than as it fits conveniently onto a chart. Because the first thing that becomes clear when you look at the belt with any care is that it does not look anything like the picture. The solar system diagram most people carry in their minds is a flat, two-dimensional image, the sun at the center, planets arranged in tidy concentric rings, and the Kuiper Belt as the outermost ring of all. A thin band of debris sitting neatly at the edge of everything. It is a convenient image, it fits on a page, it communicates relative position clearly and without confusion. But diagrams compress space in ways that fundamentally distort the thing being shown. Every diagram of the solar system is a lie of scale. The distances between objects are reduced by factors of millions. The sizes of planets are exaggerated by factors of thousands, and the three-dimensional volume of space is collapsed into two flat dimensions. The diagram is useful the way a map is useful. It tells you where things are relative to each other, but it tells you almost nothing about what it actually feels like to exist in that space. The Kuiper Belt, in reality, is not a thin ring. It is a thick, three-dimensional torus, a donut-shaped region of space extending not just outward from Neptune, but also above and below the plane of the solar system by significant distances. Objects in the belt do not all orbit in the same flat plane as the planets. Their orbits are inclined, tilted, sometimes dramatically so. The belt has vertical extent. It has depth in all three spatial dimensions, and it is vast in ways that the diagram cannot communicate. The inner edge of the classical Kuiper Belt sits at roughly 30 astronomical units from the Sun, just beyond Neptune's orbit. The outer edge of the classical belt extends to approximately 50 astronomical units. That is a radial width of 20 astronomical units, 20 times the distance between the Earth and the Sun. In kilometers, that is roughly 3 billion kilometers of radial depth. Not the width of the belt as seen from above, which is larger still. Just the depth measured outward from the Sun. To cross that distance at the speed of New Horizons, one of the fastest spacecraft ever launched, would take years. The belt is not something you pass through quickly. It is something you are inside of for a very long time. That scale, felt properly rather than simply noted, begins to change what the word dangerous means in this context. The danger of the Kuiper Belt is not compressed into a single narrow ring where collisions are frequent and inescapable. It is distributed across a volume of space so immense that the emptiness within it is almost total. And that combination, vast scale, distributed population, almost total emptiness, is precisely what makes it so difficult to navigate safely. The emptiness is real. But so is what fills it. The image of the Kuiper Belt as a single, unified ring of icy debris is not simply incomplete. It is a misrepresentation of something considerably more layered and more strange. What astronomers actually describe when they speak carefully about the belt is not one population of objects, but several distinct dynamical families, each with different orbital histories, different compositions, different relationships to Neptune, and different implications for anything that tries to pass through them. Understanding why the belt is more dangerous than it looks requires understanding this architecture. Not the surface image, but the structure beneath it. The first population is what astronomers call the classical Kuiper Belt objects. These are the objects most people imagine when they think of the belt. Bodies orbiting the Sun at distances between roughly 42 and 48 astronomical units, following orbits that are relatively circular and relatively close to the plane of the solar system. Within this population, there are two distinct subgroups, which astronomers somewhat informally call the cold classicals and the hot classicals, names that refer not to temperature, but to orbital behavior. The cold classical objects have nearly circular orbits with low inclinations. They sit close to the plane of the solar system, they move in orderly paths, and they appear to have remained largely undisturbed since the early solar system. Many of them are binary, two objects orbiting each other, and their binaries are wide and fragile, the kind that would not survive a turbulent dynamical history. They are, in a sense, the most pristine material in the solar system. Untouched, unchanged, sitting in the cold and dark in almost exactly the configuration they occupied 4 billion years ago. The hot classicals are different. They have more eccentric orbits, higher inclinations, and a dynamical history that suggests they were scattered into their current positions by gravitational interactions with Neptune during the early solar system. They are not pristine. They are the survivors of a violent reorganization. Objects that were pushed and pulled and stirred by a Neptune that was not always where it is today. And then there are the resonant objects. These are KBOs whose orbital periods are locked in precise mathematical relationships with Neptune's orbital period. The most famous example is Pluto, which orbits the Sun exactly twice for every 3 times Neptune completes an orbit, a 3-2 resonance. This resonance is not accidental, and it is not fragile. It is a gravitational lock that has persisted for billions of years, stabilizing Pluto's orbit even though that orbit crosses Neptune's path. Objects in the 3-2 resonance are called plutinos, and there are hundreds of them. There are also objects in the 2-1 resonance, the 5-3, the 4-3, and several others, each representing a population of bodies that Neptune's gravity has organized into specific orbital families. These resonances matter for understanding the belt's danger, because they tell you something important. The belt is not a random scattering of objects drifting freely through space. It has structure. It has gravitational architecture. Neptune has sorted its population over billions of years into organized families, and those families have boundaries, and crossing those boundaries. Moving from one resonant population into another means passing through regions where orbital dynamics change in ways that are not always predictable on human timescales. Beyond the classical belt and the resonant objects, there is a third major population, the scattered disk. The scattered disk objects have highly eccentric, highly inclined orbits that take them far out into the solar system. Some with aphelion distances of hundreds of astronomical units before swinging back in toward the Sun. They are the most dynamically active population in the outer solar system, and they are the primary source of the short-period comets that occasionally pass through the inner solar system and become visible from Earth. The scattered disk blurs into the classical belt on one end and into the even more distant detached objects on the other, bodies like Sedna, whose orbit carries it so far from the Sun that no known planetary body could have perturbed it into its current path. The architecture of the belt, in this sense, does not have a clean outer edge. It fades. It grades outward from the classical belt into the scattered disk, into the detached objects, into the inner Oort cloud, each transition a softening of density and an increase in orbital strangeness. And throughout all of this, the classical objects, the resonant populations, the scattered disk, the detached bodies, the sun is growing fainter and its warmth is fading toward nothing. At 40 astronomical units from the sun, which is roughly the middle of the classical Kuiper Belt, the sun is not the brilliant disk of light that fills the sky on Earth. It is a star, a bright star, the brightest star in the sky by a large margin, still far more luminous than anything else visible in that dark, but a star nonetheless. A point of light, not a presence. Its warmth at that distance is approximately 1,600 times weaker than what reaches the surface of the Earth. The temperature of objects in the belt hovers around minus 220 degrees Celsius. That is cold enough to freeze not just water, but nitrogen, carbon monoxide, methane. The surfaces of Kuiper Belt objects are coated in ices of these volatile compounds, tinted reddish or grayish by billions of years of exposure to cosmic radiation. Nothing in the Kuiper Belt is warm. Nothing there is lit by anything brighter than a very distant star. And in that cold, dim, expansive volume of space, hundreds of thousands of objects drift along their long, slow orbits, most of them never having been close to anything else in billions of years. The architecture of the belt, its multiple populations, its resonant structure, its blurred outer boundary, its vast three-dimensional extent, is the foundation for understanding everything that makes it genuinely hazardous. Not hazardous in the way an asteroid field in a film is hazardous, with constant near misses and dramatic evasive maneuvers. Hazardous in a quieter, more structural way. Hazardous because of what it contains, how much of it remains unseen, and what happens when the invisible and the moving occupy the same space. The asteroid belt, which sits between Mars and Jupiter, is the comparison most people reach for when trying to picture the Kuiper Belt. It is a misleading comparison in almost every respect. The asteroid belt contains a total mass equivalent to roughly 4% of the Moon. The Kuiper Belt contains somewhere between 20 and 200 times more mass than that. Estimates vary, but the belt is substantially more massive than the asteroid belt in total material. The asteroid belt is also far more compact, far closer to the sun, and far better illuminated. The Kuiper Belt is colder, darker, larger in every dimension, and far less completely surveyed. What the asteroid belt comparison does get right is the general idea of a region populated by small bodies rather than a single large one. But the Kuiper Belt's small bodies are icy rather than rocky, its dynamics are shaped by a different planet, its populations are more diverse, and its sheer volume means that even a dense concentration of objects in one region can be separated from another dense concentration by distances that dwarf anything in the inner solar system. The belt is not a ring. It is a wilderness. And like any wilderness, what makes it dangerous is not the things you can see. It is the things you cannot. There is a particular kind of deception built into every diagram of the Kuiper Belt ever published. It is not an intentional deception. It is a necessary one, the unavoidable consequence of trying to represent a three-dimensional volume of space billions of kilometers across on a flat surface that fits in a textbook or on a screen. But the effect of that deception is real, and it shapes how almost everyone thinks about what the belt actually is. On the diagram, the belt looks crowded. The dots representing known objects are clustered together in a broad band beyond Neptune, dense enough to suggest a region where objects are relatively common, where a spacecraft passing through would regularly encounter something, where the danger of collision feels intuitively plausible. The diagram creates a felt sense of density, of presence, of a region that is genuinely full of things. The reality is almost the exact opposite. The Kuiper Belt is by any meaningful measure nearly empty. The average distance between objects in the belt, not between the largest and most prominent ones, but between typical belt objects of modest size, is measured in tens of millions of kilometers. In some regions, the average separation is considerably larger than that. For context, the distance between the Earth and the Moon is roughly 384,000 kilometers. The average gap between Kuiper Belt objects is often 100 times greater than that distance, sometimes 1,000 times greater. New Horizons flew through the heart of the Kuiper Belt for years. It traveled billions of kilometers through the region that the diagram depicts as a crowded band of debris. And in all of that travel, in all of those billions of kilometers, it never came meaningfully close to a significant collision. The mission planners did identify a small number of potential hazard zones near the Pluto flyby, regions where debris from Pluto's moons might have created a thin shell of material around the system, and they analyzed the risk carefully. But the risk from the belt itself, the vast field of debris that the diagram suggests should be everywhere, was not the limiting factor for the mission. The belt was, in practice, almost completely navigable, almost perfectly empty. This is not a paradox. It is simply a matter of scale. When the volume of space is large enough, even hundreds of thousands of objects distributed through it produce an average separation that is enormous. The belt's objects are real, and they are numerous, and they are genuinely distributed through that region of the solar system. But the region itself is so vast that the objects within it barely register as a presence in the volume they occupy. Consider what it would mean to compress the Kuiper Belt's population into the surface area of the Earth. If you took every known Kuiper Belt object larger than 100 kilometers across, approximately 100,000 of them, and distributed them uniformly across the surface of the Earth, each one would have roughly 5 square kilometers of Earth surface to itself. 5 square kilometers, the size of a small town. That is the density of the Kuiper Belt expressed in human terms. Objects that size, separated by distances equivalent to small towns, drifting slowly in an ocean of space. The diagram cannot show you this. The diagram can only show you the presence of objects, not the absence that surrounds them. And so the belt appears crowded, and the word dangerous attaches to it in the way danger attaches to crowded things, as collision risk, as constant threat, as the sensation of moving through a space where something is always nearby. But the danger of the Kuiper Belt is not the danger of proximity. It is the danger of invisibility. Because while the average separation between belt objects is enormous, and while a spacecraft can travel through the belt for years without coming close to anything large, the objects you cannot see are a different matter entirely. The catalog of known Kuiper Belt objects is not a complete census of the belt's population. It is a sample, a partial survey, limited by the sensitivity of our instruments and the geometry of our observations, that has captured some fraction of the belt's true population and left the rest undetected. The objects we have found are, almost without exception, the largest ones, the brightest ones, the ones close enough to reflect enough sunlight to register on the detectors of the telescopes that have searched the sky. Objects smaller than roughly 100 kilometers across, which is to say, the vast majority of the belt's population by number, are largely invisible to current surveys at Kuiper Belt distances. They are too small, too dark, and too far away to detect with existing technology. The orbital models that describe the belt's dynamics predict that the total number of objects in the belt, larger than 1 kilometer across, runs into the billions. Billions of objects, of which we have found a tiny fraction. The rest drift in the dark, unseen, unmapped, their positions unknown, and their future trajectories uncalculated. This is the density illusion's true consequence. The diagram suggests crowding that doesn't exist in the large object population. But in the small object population, in the dust, the fragments, the sub-kilometer bodies produced by 4 billion years of slow collisions and gravitational grinding, the belt may be considerably more populated than the diagram suggests, in ways that are precisely the hardest to detect and the most hazardous to encounter. A spacecraft passing through the belt is not at significant risk from the large catalogued objects. Their positions are known well enough, and the belt is empty enough that the probability of a chance encounter is vanishingly small. The risk comes from the uncatalogued small objects, from the dust, from the debris halos that surround large KBOs, produced by collisions over geological time and extending invisibly outward from each body into the surrounding space. When New Horizons passed through the Pluto system, mission controllers were genuinely uncertain about the density of debris in that region. Pluto has 5 known moons: Charon, Styx, Nix, Kerberos, and Hydra, and the gravitational interactions between these bodies could plausibly have produced a debris field capable of damaging the spacecraft. The team ran hazard assessments. They identified a safe corridor through the system. They prepared contingency trajectories. The concern was real enough that NASA publicly discussed the possibility of rerouting the spacecraft. In the end, the Pluto system proved navigable. The debris density was lower than the worst-case models had suggested. New Horizons passed through safely, collected its data, and continued outward into the belt, but the exercise illustrated something important. The danger in the Kuiper Belt is not the danger you can map. It is the danger you cannot. It is the objects beneath the detection threshold, the debris clouds around bodies we have never visited, the small fragments following orbits we have never calculated. The diagram shows you the belt as a region of presence. The real belt is a region where the presence is mostly hidden, and the hidden part is the part that matters. The emptiness of the belt is real. Any spacecraft traveling through it will spend the vast majority of its time in essentially empty space, with nothing nearby of any significance. But the emptiness is not complete. And in a region where rescue is impossible, where any damage to critical systems means the end of the mission or the end of a crew, the small probability of encountering something unseen is not a small concern. It is the central one. The belt looks empty because we can only see the large things, and the large things are genuinely sparse. What we cannot see is something else entirely. And what we cannot see is by definition exactly what we cannot avoid. Every catalog has an edge, a point beyond which the list stops, not because there is nothing left to list, but because the instruments that built the catalog could not see any further. The catalog of Kuiper Belt objects has that edge, and it sits much closer to the beginning of the true population than most people realize. What we have found in the belt, as of the most recent surveys, numbers in the thousands of confirmed objects. Several thousand trans-Neptunian bodies with measured orbits, classified dynamical families, estimated sizes, and some degree of compositional characterization. A few dozen of these are large enough to be considered dwarf planets or dwarf planet candidates: Pluto, Eris, Makemake, Haumea, Quaoar, Sedna, and a handful of others. Below those are hundreds of objects in the 100 to 500 kilometer size range, and below those, the catalog thins rapidly as objects become too small and too dark to detect at Kuiper Belt distances. This catalog feels substantial. Thousands of objects is not nothing. But when you place it against the backdrop of what the orbital models predict must exist, the catalog begins to look very thin indeed. The predictions come from two sources: dynamical modeling and size distribution theory. Dynamical modeling uses our understanding of how the belt formed and evolved, how Neptune scattered its original population, how collisions ground large objects into smaller ones, how gravitational resonances organized the surviving material, to estimate how many objects should be present in various size ranges. Size distribution theory uses the observed population of large objects whose distribution follows a predictable mathematical pattern to extrapolate downward to smaller sizes. Both approaches arrive at similar conclusions. The number of Kuiper Belt objects larger than 100 kilometers across is estimated at roughly 100,000. That is a round number, and it carries real uncertainty, but it is broadly consistent across multiple independent estimation methods. Of those 100,000 objects, we have found and cataloged somewhere between 1 and 2%. The remaining 98 or 99% are out there, their existence predicted by the models, their positions unknown, their surfaces never observed by any instrument. Below 100 kilometers, the numbers grow rapidly. The size distribution of small bodies in the outer solar system follows what is called a power law. For every object of a given size, there are many more objects of half that size, and vastly more of quarter that size. The exact slope of this power law in the Kuiper Belt is uncertain, because directly observing sub-100 kilometer KBOs at belt distances is at or beyond the limit of current technology. But estimates for the number of belt objects larger than 1 kilometer across run into the billions. Some models suggest tens of billions of objects in a region of space we have cataloged to roughly 1% completeness for the largest fraction of that population. The catalog is not a map of the belt. It is a faint tracing of the belt's most visible features, with almost everything else remaining in the dark. The detection problem is fundamental, not incidental. It is not the case that better telescopes would quickly resolve it, although better telescopes help at the margins. The problem is that Kuiper Belt objects are dark, cold, and far away, which means the amount of sunlight they reflect is tiny by the time it reaches Earth. The albedo of typical KBOs, the fraction of incoming sunlight they reflect, is very low. Many KBOs reflect only a few percent of the light that strikes them. Their surfaces are coated in dark, radiation-processed organic compounds called tholins, produced by billions of years of exposure to cosmic rays and ultraviolet radiation from the distant sun. A typical KBO is, in terms of reflectivity, closer to a lump of charcoal than to a mirror. A 50-kilometer KBO at 45 astronomical units from the sun, with an albedo of 5%, produces a signal at Earth that is close to the detection limit of the largest ground-based telescopes currently in operation. Objects smaller than that, or darker than that, or farther away than that, are simply invisible to current surveys. They exist, the models are confident of this, but they are beyond our ability to find individually. The most ambitious recent effort to characterize the outer solar system population was the Outer Solar System Origin Survey, known as OSOS, which ran from 2013 to 2017 using the Canada-France-Hawaii telescope. OSOS was designed with exceptional care to account for survey biases, the tendency of any search to preferentially find objects that are easier to detect, which then skew the apparent population distribution. By characterizing exactly what the survey was and was not sensitive to, The Ossos team could make more reliable inferences about the true underlying population. The results confirmed the broad picture while adding important detail. The classical belt's total population was refined. The relative sizes of the different dynamical populations were better constrained. And the survey reinforced the conclusion that had been building for years: the known population of Kuiper Belt objects is a small and somewhat biased sample of the true population. And the true population is far larger and far less understood than the catalog suggests. What this means in practical terms for anything traveling through the belt is not that the large, unknown objects represent a primary hazard. The belt is still too empty for chance encounters with major bodies to be a significant concern. What it means is that the smaller objects, the sub-kilometer fragments that the models predict in such large numbers, represent a background hazard that cannot be mapped or avoided because it cannot be detected. Think of it this way. When a spacecraft passes through the inner solar system, mission controllers can calculate its trajectory with extraordinary precision and compare it against a catalog of known objects to identify any potential close approaches. That catalog, for near-Earth objects and main belt asteroids, is reasonably complete at the sizes that could damage a spacecraft. The catalog is not perfect, and new objects are found regularly, but it provides a meaningful basis for hazard assessment. In the Kuiper Belt, that basis essentially does not exist below the 100-kilometer scale. A spacecraft traveling through the belt is passing through a population of objects that cannot be mapped at the relevant hazard sizes. The trajectory can be calculated. The known large objects can be avoided. But the unknown population, the billions of kilometer scale and sub-kilometer objects that the models predict must exist, is simply invisible. It is not in any catalog. It cannot be placed in any hazard assessment. It is a fixed background of uncertainty through which anything in the belt must travel without any detailed knowledge of what is there. This would be a manageable problem in a region where, if something went wrong, repair or rescue were possible. In the inner solar system, a spacecraft that suffers damage from an unexpected impact can, in some scenarios, be reached by a repair mission. The timeline is long, but not infinite. A spacecraft at 40 astronomical units from Earth, traveling through the Kuiper Belt, is in a fundamentally different situation. No repair mission is possible on any human timescale. If something goes wrong, if a critical component is damaged, if a sensor is destroyed, if a navigation system fails, the spacecraft is on its own. The object that caused the damage remains unknown. The damage cannot be repaired from Earth. The mission, or in the case of a crewed spacecraft, the crew, faces the consequences of an encounter with something that was never in any catalog and could never have been predicted. The object problem is not a temporary gap in our knowledge, waiting to be filled by the next generation of telescopes. It is a structural feature of the belt, a consequence of the physics of detection at those distances, combined with the sheer number of objects the belt contains. Even surveys that go dramatically deeper than any current instrument would find the catalog growing slowly, because each improvement in sensitivity adds objects in a size range where the numbers are far larger and the individual objects are far fainter. The belt is full of things we cannot see. It will remain full of things we cannot see for a very long time. And anything that travels through it does so with the knowledge that the map it carries is fundamentally incomplete, that the territory it shows accounts for only a fraction of what is actually there. There is a particular quality to that kind of incompleteness. It is not the incompleteness of a map with blank spaces marked unknown, spaces that invite exploration and promise eventual filling. It is the incompleteness of a map that looks finished, that shows thousands of objects in their catalogued positions, but that is missing the vast majority of what exists in precisely the size range most relevant to safety. The catalog is a comfort. And like most comforts built on incomplete information, it is more reassuring than the situation warrants. When most people imagine a collision in space, they imagine something sudden, something dramatic, a high-velocity impact, a flash of energy, a cloud of expanding debris. The images come from planetary science documentaries, the Chicxulub impactor striking the Yucatan Peninsula, the collision that formed the moon, the late heavy bombardment scarring the inner planets. These are the collisions that register in the imagination. Violent, fast, transformative, the collisions that shaped the Kuiper Belt are nothing like that. They are slow. By the standards of inner solar system dynamics, they are almost gentle. And it is precisely their slowness, their geological patience, their tendency to grind rather than shatter, that makes the debris they produce so difficult to detect and so hazardous to encounter. Objects in the Kuiper Belt move slowly relative to each other. At 40 astronomical units from the Sun, orbital velocities are low. Objects in the classical belt orbit at roughly 1 to 2 kilometers per second. At those orbital speeds, the relative velocity between two nearby objects, the speed at which they might approach each other and collide, is typically a few hundred meters per second, sometimes less. This is fast by everyday human standards, but in the context of the solar system, it is very slow. Main belt asteroids collide at velocities of 5 kilometers per second or more. Near-Earth objects can strike Earth at velocities exceeding 30 kilometers per second. By those measures, Kuiper Belt collision velocities are sedate. Slow collisions do not produce the dramatic shattering that high-velocity impacts create. When two objects meet at a few hundred meters per second, the outcome depends strongly on their sizes, compositions, and internal structures. But the general tendency is toward cratering, chipping, and abrading rather than catastrophic disruption. Material is removed from both surfaces. Ejecta are launched at low velocities relative to the objects involved. Over time, repeated low-velocity collisions grind the surfaces of KBOs, produce small fragments that drift away from both objects, and slowly reduce the overall population of larger objects while increasing the population of smaller ones and dust. This grinding process has been operating in the Kuiper Belt for approximately 4 billion years. 4 billion years of slow, patient collision, objects drifting close, grazing each other, chipping material off surfaces, sending fragments on slightly different orbits that then drift into other objects and chip fragments off them in turn. The cumulative product of 4 billion years of this process is not a field of large boulders sitting in open space. It is a subtle, pervasive background of small fragments and dust distributed throughout the belt in a way that reflects the collision history of each region. The distinction between cold classical KBOs and hot classical KBOs matters here again. The cold classicals, with their nearly circular low inclination orbits, have very low relative velocities. The collisions in that population are even slower and gentler than the belt average. The hot classicals, with their more eccentric and more inclined orbits, have higher relative velocities and correspondingly more energetic collisions. The scattered disk objects, with their dramatically eccentric orbits, can collide at speeds that approach the more energetic end of the belt's dynamical range. Each population has its own collision economy, its own characteristic frequency and energy of impacts, its own debris production rate, its own contribution to the belt's background of small fragments. The belt is not dynamically uniform. It is a patchwork of regions with different collision histories and different debris environments, none of which is completely characterized by current observations. Around every large cabo, every object of significant size that has persisted through billions of years of this slow grinding, there is a debris environment shaped by its own history and the history of the objects that have struck it. Impact ejecta from every collision that has ever occurred on that object's surface has been launched into the surrounding space at low velocity. Some of this ejecta escapes the object's gravity entirely and drifts away into the belt. Some of it remains in orbit around the object as a debris halo. Some of it re-impacts the surface after years or decades. The net effect is that large KBOs are surrounded by invisible halos of fine material, fragments, dust grains, molecular ices that extend for distances many times larger than the objects themselves. These halos have never been directly observed. At Kuiper Belt distances, they are far too faint. Their existence is inferred from dynamical modeling and from what we know about collision physics. But they are real, and they represent a hazard that is specifically invisible, not the hazard of a large object with a known position, but the hazard of a diffuse cloud of material surrounding every significant cabo in the belt. The New Horizons mission gave scientists a first-hand glimpse of this problem when it approached Pluto. The Pluto system's 5 moons are collision products, almost certainly the result of a large impact that knocked material off Pluto's surface billions of years ago. That impact and the subsequent evolution of the debris produced not just the 5 named moons, but a population of smaller fragments in the system that was genuinely uncertain in density before the flyby. The mission designers had to treat the region around Pluto as a potential debris field and plan the flyby accordingly. In the end, the field was navigable. But the uncertainty was real and the caution was warranted. Multiply that uncertainty by every large cabo in the belt. Every object with a history of collisions, which is to say, every object in the belt, without exception, is surrounded by an environment shaped by that history in ways that cannot be fully characterized from Earth. There is one further consequence of the belt's slow collision economy that is worth sitting with. The dust produced by 4 billion years of grinding does not simply accumulate in place. Dust grains in the outer solar system are subject to a force called the Poynting-Robertson effect. The pressure of solar radiation, which causes small particles to spiral slowly inward toward the sun over long timescales. This means the dust produced in the Kuiper Belt migrates slowly and continuously inward through the solar system. The outer solar system is not a static debris field. It is a slowly flowing system, with new material being produced at the belt and old material drifting inward over millions of years. The practical consequence for spacecraft is that the dust environment in the outer solar system is not simply a local property of wherever the spacecraft currently is. It is the accumulated product of debris generated across the entire belt, redistributed by radiation pressure over time. A spacecraft traveling inward from the belt toward the inner solar system would encounter gradually increasing dust densities as it moved through regions where inward migrating belt debris has been concentrating. None of this rises to the level of catastrophic hazard in normal operation. Spacecraft crossing the outer solar system do so regularly, and the dust environment, while non-trivial, is not a primary mission risk in most scenarios. But each grain of dust moving at relative velocity carries energy proportional to the square of that velocity. A grain of sand-sized particle barely visible to the naked eye on Earth, hitting a spacecraft component at even a modest relative velocity carries enough energy to damage or destroy a sensor, hit a solar panel, or compromise a thermal shield. Over a journey of years through the belt, many such encounters accumulate. Each one alone is survivable. Their sum, over time, is a slow erosion of the spacecraft systems, a gradual accumulation of small damages that individually register as nothing significant and collectively represent a steady reduction in capability. The collision economy of the Kuiper Belt does not threaten a spacecraft with sudden catastrophe. It threatens it with something quieter and harder to measure: the slow, patient, cumulative consequence of 4 billion years of grinding, distributed through a volume of space that no survey has fully characterized and no instrument has fully mapped. The Kuiper Belt is easy to think of as a relic, something ancient and static, a fossil record of the early solar system preserved in cold storage beyond Neptune. That image is not entirely wrong. The belt does contain material that has remained largely unchanged since the solar system formed, and studying it does offer a kind of window into the conditions that existed 4.5 billion years ago. In that sense, it is genuinely ancient. But ancient is not the same as static. And the belt's history is not a history of preservation. It is a history of violence, a history of reorganization, scattering, and bombardment on a scale that reshaped the entire solar system and left its mark on every world we know. Understanding the belt's bombardment record is not simply a matter of historical interest. It is essential for understanding what the belt is today, what populations it contains, why those populations are distributed the way they are, and what the belt will continue to do to the inner solar system in the billions of years ahead. The story begins in the early solar system, roughly 4 billion years ago. The giant planets, Jupiter, Saturn, Uranus, and Neptune, had formed and were settling into their orbits. The region beyond Neptune was more densely populated than it is today, containing a mass of small icy objects perhaps 10 to 20 times greater than the belt's current mass. And the giant planets were not yet in the positions we find them today. They were closer together, and their orbits were still evolving under the influence of their mutual gravitational interactions and the gravitational drag produced by the dense disk of small bodies surrounding them. What happened next is described by a theoretical framework known as the Nice model, named for the city in France where the team that developed it was based. According to this model, the giant planets underwent a period of orbital instability. Jupiter moved inward slightly. Saturn, Uranus, and Neptune moved outward. Neptune, in particular, migrated significantly, drifting outward through the disk of small bodies that would eventually become the Kuiper Belt, scattering most of them as it went. The consequences of Neptune's migration were profound. As Neptune moved outward, its gravitational resonances swept through the disk like a slow wave, capturing some objects into stable resonant orbits, the Plutinos and other resonant populations that persist today, while ejecting the majority of objects onto highly eccentric orbits that took them into the inner solar system or out of the solar system entirely. The belt's original population was dramatically reduced, the survivors sorted into the dynamical families we observe today, and a massive flux of icy debris was unleashed toward the inner solar system. This flux is what geologists and planetary scientists call the Late Heavy Bombardment, a period roughly 3.9 billion years ago, marked in the cratering records of the Moon, Mercury, and Mars by an elevated rate of large impacts. The evidence is written in craters. The Moon's highlands, the ancient, densely cratered terrain that dominates its surface, preserve the record of this bombardment in rock. The large impact basins, Mare Imbrium, Mare Serenitatis, Orientale, date to this same period. So do many of the large craters on Mercury and the ancient cratered terrain on Mars. The source of this bombardment is debated. Some models suggest it was primarily the product of the asteroid belt being stirred by Jupiter's resonances. Others point to the Kuiper Belt as the primary reservoir, with the wave of icy projectiles produced by Neptune's migration delivering impacts to the inner solar system on timescales consistent with the geological record. The question is not fully resolved, but the Kuiper Belt was certainly a participant, a major source of the icy bodies that crossed the inner solar system during this violent period. The Earth was struck too during the late heavy bombardment. The evidence is harder to read here because Earth's geological activity has erased most of the ancient cratering record. But the lunar record provides a proxy. What struck the moon struck the Earth in proportion to their sizes in gravitational cross-sections, and the Earth, larger and gravitationally more attractive, would have received a substantially higher flux of impacts than the moon during any bombardment period. This matters not just as history. It matters because the belt is still doing what it did during the late heavy bombardment, only more slowly. Neptune's gravitational resonances are still operating on the belt's population, still slowly perturbing objects out of stable orbits and onto eccentric paths. The rate is far lower than it was 4 billion years ago. The belt has lost most of its original mass, and the remaining population is dominated by objects that have survived in stable orbits for billions of years. But the reservoir has not been emptied, and the pump has not been turned off. The short-period comets that pass through the inner solar system, the comets with orbital periods shorter than 200 years, the ones that become periodically visible from Earth, are the modern expression of this ongoing process. They are Kuiper Belt objects that have been perturbed by Neptune's gravity onto eccentric orbits that bring them into the inner solar system, where the sun's heat vaporizes their surface ices and produces the characteristic coma and tail that makes them visible. Jupiter family comets, the largest category of short-period comets, are almost certainly KBOs that have been captured into shorter period orbits by Jupiter's gravity after entering the inner solar system from the belt. These comets are the belt's ambassadors to the inner solar system, objects that traveled outward in the early solar system, spent billions of years in cold storage beyond Neptune, and are now under the slow influence of gravitational perturbations, making their way back inward. They are direct samples of belt material, and studying their compositions gives planetary scientists a window into the chemistry of the early outer solar system. But the comets are also a reminder that the belt's influence on the inner solar system is ongoing. The reservoir is still draining. Objects are still being perturbed out of the belt on timescales of millions of years. Some of them become comets. Some of them become centaurs, objects on unstable orbits between Jupiter and Neptune, intermediate between the belt and the inner solar system, destined eventually to either become comets, collide with a planet, or be ejected from the solar system entirely. The belt, in this sense, is not a closed system. It is a source, a slowly leaking reservoir of material that has been delivering icy bodies to the inner solar system for 4 billion years and will continue to do so for billions more. The bombardment record written in the craters of the moon is not a closed chapter in the solar system's history. It is the most visible signature of a process that is still operating at a lower rate right now. Understanding this changes the way you think about the belt's danger. The danger is not simply local. not simply the hazard facing a spacecraft that passes through the belt's volume. It is also directional, flowing inward from the belt toward the inner solar system, manifesting on timescales of millions to billions of years as the occasional comet or larger impactor that finds its way from the cold outer darkness to the warmer, more inhabited regions of the solar system. The belt is not finished with the inner solar system. It has been delivering material to the worlds of the inner solar system since before the Earth had oceans. It will continue to deliver that material long after any civilization that might be watching has run its course. The ancient debris field beyond Neptune is not a relic of past violence. It is an active participant in the solar system's ongoing story. And the story, as always, involves impacts. There is a common way of imagining Neptune's relationship to the Kuiper Belt. In this picture, Neptune sits at the inner edge of the belt, a large planet marking the boundary between the planetary solar system and the outer wilderness. Its gravity acting as a kind of wall that keeps the belt's objects from drifting inward. Neptune as guardian, Neptune as the edge. This picture is wrong in almost every respect. Neptune does not guard the belt. Neptune is the belt's primary destabilizing force, the gravitational engine that has been slowly reorganizing, scattering, and ejecting belt objects for billions of years and continues to do so now. Its relationship to the belt is not the relationship of a wall to a room. It is the relationship of a hand to a puzzle, slowly and continuously rearranging the pieces. Understanding Neptune's gravitational influence on the belt, what it does to orbits, how it operates over time, and why it makes the belt a more dangerous and more dynamic place than it appears, requires understanding two gravitational mechanisms that operate in the outer solar system on very different timescales, but with similarly profound consequences. The first is mean motion resonance. A mean motion resonance occurs when two objects have orbital periods that stand in a simple mathematical ratio, 2 to 1, 3 to 2, 4 to 3, and so on. When this ratio holds precisely, the two objects repeatedly encounter each other at the same points in their orbits, and the gravitational kicks they exchange accumulate rather than canceling out. The result over time can be either stabilizing or destabilizing, depending on the specifics of the resonance. Neptune maintains several powerful mean motion resonances in the Kuiper Belt. The 3.2 resonance, which captures Pluto and the Plutinos, is a stabilizing one. Objects in this resonance are protected from close encounters with Neptune by the geometry of the resonance itself, which ensures that when their eccentric orbits bring them closest to the Sun, Neptune is always far away. The resonance is a refuge. But other resonances are less kind. The 2-1 resonance, sitting at around 47.8 astronomical units, is a zone of instability for many objects. Objects that drift into the 2-1 resonance can have their orbital eccentricities pumped up over time, eventually reaching orbits that bring them into the inner solar system as comets or centaurs. The 5.3, the 4.3, and other resonances each have their own dynamical character, some stabilizing, some destabilizing, some capable of dramatically altering an object's orbit on timescales of tens of millions of years. The practical consequence of this resonance structure is that the Kuiper Belt is not dynamically uniform. It has specific zones of instability, regions where objects are being slowly accelerated onto more eccentric orbits, gradually moving them out of the belt and into the rest of the solar system. These zones are not dangerous in the immediate kinetic sense. Passing through a mean motion resonance zone is not like passing through a debris field. but they are dynamically active in a way that makes the belt's population inherently unstable over long timescales, constantly supplying the inner solar system with objects from its reservoir. The second mechanism is more subtle and operates on even longer timescales. It is called the Kozai-Lidov mechanism, named for the two astronomers who independently described it in the 1960s. The Kozai-Lidov mechanism operates on objects with highly inclined orbits that are tilted significantly relative to the plane of the perturbing body, in this case Neptune. When an object's orbit is inclined at a sufficient angle, it experiences a long period oscillation in which its orbital eccentricity and inclination trade off with each other over timescales of millions of years. The practical effect is this: an object in a moderately eccentric, moderately inclined orbit can, under the Kozai-Lidov mechanism, gradually evolve into a highly eccentric, low inclination orbit, or vice versa, without any close encounter with Neptune. The orbit changes slowly, driven by the average gravitational effect of Neptune over many orbits, but the change is real and can be dramatic. An object that appears to be in a stable orbit today may, in 100 million years, be on an orbit that brings it into the inner solar system. This has two implications. The first is that the belt's long-term population is more unstable than its current snapshot suggests. Objects that appear stable today are not necessarily stable over geological timescales. Their orbits may be slowly evolving under Kozai-Lidov dynamics toward configurations that will eventually move them out of the belt. The belt we see today is a moment in a continuous process of slow gravitational evolution, not a permanent steady state. The second implication is more subtle. The Kozai-Lidov mechanism makes the belt's danger partially invisible in a different sense than the detection problem discussed earlier. It is not that the hazardous objects are too small to see. It is that the objects whose orbits are currently stable may not remain so, and the timescales on which they will change are long enough that current observations cannot reliably identify which ones are on the path to instability. Neptune's gravity, in other words, creates a belt whose future is not fully predictable from its present configuration. The orbits of belt objects are not fixed. They are slowly evolving under the influence of resonances, Kozai-Lidov dynamics, and other perturbations, in ways that will gradually change the belt's population on timescales of tens to hundreds of millions of years. For anything passing through the belt on human timescales, this long period instability is not a direct hazard. The orbital changes are far too slow to matter over the months or years of a spacecraft transit. But it reinforces the fundamental character of the belt as a place that is not as quiet as it appears. The surface stillness, the slow orbital velocities, the vast separations between objects, the apparent stability of the catalogued populations, conceals a deeper dynamical activity that has been continuously reshaping the belt for 4 billion years. There is another gravitational effect worth noting, one that operates not on belt objects themselves, but on the space between them. The region of the Kuiper Belt is not simply subject to Neptune's gravity. It sits within the gravitational field of the entire solar system. Jupiter, Saturn, Uranus, and Neptune all contribute to the background gravitational environment of the outer solar system. Their combined influence creates a complex, time-varying gravitational landscape in which simple, stable orbits are relatively rare, and in which small perturbations can accumulate over long timescales into significant orbital changes. A spacecraft traveling through this landscape is not simply a passive observer of belt dynamics. Its trajectory is itself affected by the gravitational field, by the same resonances and perturbations that affect belt objects. Mission designers must account for these effects when planning long-duration missions through the outer solar system. The trajectory that looks optimal at launch may, over years of travel, require correction as accumulated gravitational perturbations push it subtly off course. Neptune does not sit at the edge of the belt as a guardian. It sits at the inner boundary as an architect, the primary force that has shaped the belt's structure, sorted its populations, organized its resonances, and continues to slowly drain its reservoir into the rest of the solar system. Its gravity reaches through the belt not as a barrier, but as a continuous presence, touching every object in the belt on every orbit, quietly rearranging the pieces on timescales that dwarf any human institution and most human concepts of time. The belt is not static, it is governed, and the governor is not gentle. Before July 2015, Pluto was a known quantity, not a fully understood one. No object in the solar system is ever fully understood from a distance, but a known one. It had been observed for 85 years since Clyde Tombaugh discovered it in February 1930. Its size had been measured, roughly, its mass had been estimated. Its largest moon, Charon, had been found. Its surface had been mapped at the coarse resolution available to Earth-based telescopes, a blurry, pixelated thing showing only the vaguest hints of surface variation. From all of this, planetary scientists had built a picture of Pluto. It was a small, frozen world at the edge of the solar system, too small to retain geological activity, too far from the sun to receive the heat that drives internal processes, too ancient to have avoided complete surface saturation by 4 billion years of impacting debris. The expected image was something like Callisto, Jupiter's outermost Galilean moon, a heavily cratered, ancient, geologically dead surface, the record of the early solar system preserved without alteration in the cold and dark. New Horizons arrived at Pluto, traveling at approximately 14 kilometers per second. It had been traveling for 9.5 years. At that speed, and given the geometry of the flyby, it had only a few hours of close observation before Pluto and its moons fell behind. The data came in slowly. The spacecraft was so far away that transmitting everything it had recorded would take more than a year. But within hours of the flyby, the first images were enough to overturn the expected picture entirely. Pluto had mountains, not ancient, eroded mountains worn down by billions of years of slow processes, but sharp, young mountains of water ice, some rising 4 kilometers above the surrounding plains. Mountains that, by their sharpness and the absence of overlying craters, appeared to be geologically recent. Perhaps 100 million years old, perhaps younger. On geological timescales, essentially fresh. Pluto had plains. Specifically, it had Sputnik Planitia, a vast heart-shaped basin of nitrogen ice covering an area roughly the size of Texas and Oklahoma combined, sitting in a large impact depression in Pluto's northern hemisphere. The nitrogen ice in Sputnik Planitia was not static. It was divided into polygonal cells, each hundreds of kilometers across, separated by shallow troughs. These cells are the surface expression of convection, the slow, churning circulation of nitrogen ice driven by heat from below, overturning on timescales of hundreds of thousands of years. The ice is moving. Pluto's surface is geologically active. The source of that heat is not fully understood. Pluto is too small and too cold for the radioactive decay that drives geological activity on Earth to be operating efficiently at this stage of the solar system's history. One hypothesis is that Pluto contains more radioactive material than expected for a body of its composition. Another is that the large impact that created the Sputnik-Planitia Basin released enough energy to drive geological activity that persists today. A third, and perhaps the most striking, is that Pluto may have a liquid water ocean beneath its surface, kept liquid by a combination of residual internal heat and the antifreeze effect of dissolved salts or ammonia, and that the heat flux from this subsurface ocean is what drives the convection visible at the surface. A subsurface ocean on Pluto, a small frozen world at 39 astronomical units from the Sun, with no significant tidal heating from a large nearby body. In a region where temperatures hover near absolute zero, and it may harbor liquid water in its interior. The implications of this possibility extend far beyond Pluto itself. The Kuiper Belt contains hundreds of objects in a similar size range, dwarf planets and large KBOs whose internal structures have never been examined. If Pluto, the most studied of these objects, turned out to be geologically active with a possible liquid interior, what does that suggest about Eris, which is approximately the same size as Pluto and sits at an average distance of 67 astronomical units from the Sun? What about Makemake? What about Haumea with its strange elongated shape and its ring system? A ring system that was not known to exist before 2017? What about the dozens of large KBOs that have been found but never visited, never imaged at close range, never examined for the signs of internal activity that New Horizons revealed on Pluto? The answer is that we do not know. We genuinely do not know whether these objects are geologically dead or geologically active, whether their interiors are frozen solid or contain liquid layers, whether their surfaces are ancient and unchanged or young and evolving. The Pluto lesson is not that all large KBOs are geologically active. It is that we were wrong about Pluto, and we may be wrong about the others in similar ways. Pluto's moon Charon adds another dimension to this uncertainty. Charon has a vast canyon system, Argochasma, that stretches nearly 1,600 kilometers across its surface and reaches depths of up to 9 kilometers. For comparison, the Grand Canyon is roughly 446 kilometers long and about 1.6 kilometers deep. Argochasma is longer and deeper by large margins. It is the product of internal expansion. Charon's interior appears to have frozen and expanded at some point in its history, cracking the outer crust across nearly its entire circumference. This is the signature of an interior that was once at least partially liquid and subsequently froze. Charon, like Pluto, was expected to be a simple frozen object. Like Pluto, it proved to be something considerably more interesting. The Pluto system revealed not just the geological complexity of two individual objects, but the inadequacy of the models that had been used to predict what the outer solar system looks like from the inside. The models were not unreasonable. They were based on the best available physics and the best available observations. They simply could not account for the level of complexity and activity that actual observation revealed. The gap between the model and the reality was not small. That gap matters for understanding the belt's danger. If the models could miss Pluto's geological activity, its mountain ranges, its convecting nitrogen plains, its possible subsurface ocean, all of these features that fundamentally change the picture of what that world is and does, then the confidence we place in our models of the belt's other large objects must be tempered accordingly. The belt contains structures and dynamics and internal states that our models may not fully capture, because our models are built from observations that are, in most cases, far coarser than what New Horizons provided at Pluto. Pluto was supposed to be the simplest case, the most studied, the most observed, the most familiar of the large Kuiper Belt objects. And it was more complex than expected in nearly every respect. The others are less studied, less observed, less familiar. The expectation should not be that they are simpler. The Pluto lesson is, in the end, a lesson about the limits of knowledge at a distance. It is a lesson that the Kuiper Belt has been quietly offering since the first surveys revealed how incomplete the catalog was and how vast the true population must be. You can observe something for decades, theorize about it for longer, name it and classify it and assign it a place on your diagrams, and still find, when you finally arrive, that the reality is something your models could not have predicted. The belt is full of Plutos. Large objects, some of them with complex histories and internal states we have never examined. What they are doing inside their frozen surfaces in the cold and dark at the edge of the solar system remains mostly unknown. The classical Kuiper Belt ends at roughly 50 astronomical units from the Sun. This is not a clean boundary. The belt does not stop abruptly at that distance the way a shoreline stops at the ocean's edge. It thins. The density of objects decreases, the orbital characteristics of those objects change, and the region beyond 50 astronomical units grades into something different enough that astronomers give it a separate name. The scattered disk. The scattered disk is not a neat, well-defined region. It is a dynamically active, broadly distributed population of objects occupying a vast volume of space extending from roughly 50 astronomical units out to perhaps several hundred or even 1,000 astronomical units from the Sun. What distinguishes scattered disk objects from classical belt objects is not simply their distance. It is their orbital shape. Scattered disk objects have highly eccentric orbits, bringing them close to Neptune at their nearest approach and carrying them out to enormous distances at their farthest. Their orbits are not the relatively circular paths of the cold classical KBOs. They are long, stretched ellipses that carry them deep into the outer solar system and back again over timescales of millions of years. These are the objects that Neptune scattered, the survivors of the early solar system's great reorganization, thrown outward by gravitational encounters with the migrating giant planet and left on orbits that still bear the signature of that violent origin. They are, in a sense, the refugees of the belt's early history. Objects that escaped into the outer solar system and have been orbiting there ever since, following paths too eccentric to be easily classified as belt objects, but too tied to the inner solar system to be considered truly detached. The scattered disk is the primary source of the Jupiter family comets that occasionally pass through the inner solar system. Objects perturbed from their scattered disk orbits by ongoing gravitational interactions with Neptune drift inward, cross the orbit of Uranus, then Saturn, then Jupiter, where the giant planet's gravity captures them into shorter period orbits. They become centaurs. They become comets. They flare briefly as the sun vaporizes their surface ices and produces the luminous coma and tail that makes them visible from Earth. And then they fade, either vaporizing completely, colliding with a planet, or being ejected from the inner solar system back into the outer darkness. Beyond the scattered disk, the solar system's outer reaches become stranger still. There is a class of objects called detached objects, or extended scattered disk objects, bodies whose orbits never come close to Neptune, whose paths are too eccentric and too distant to be explained by Neptune's gravitational influence alone. The most famous of these is Sedna. Sedna was discovered in 2003 by Mike Brown, Chad Trujillo, and David Rabinowitz. It is a large reddish object, roughly 1,000 kilometers across, and its orbit is unlike anything else in the outer solar system. Sedna's closest approach to the Sun, its perihelion, is 76 astronomical units. That is more than twice Neptune's orbital distance, well beyond the outer edge of the classical Kuiper Belt. And its farthest point from the Sun, its aphelion, is estimated at roughly 937 astronomical units. Its orbital period is approximately 11,400 years. The problem with Sedna is that no known body in the solar system should have put it on that orbit. Neptune's gravitational influence does not reach efficiently to 76 astronomical units at that distance. Neptune cannot perturb an object's orbit in the way needed to produce Sedna's extremely elongated path. The Oort cloud, the vast spherical shell of comets at the outermost edge of the solar system, could in principle deliver objects onto orbits like Sedna's. But Sedna's orbit is too flat, too aligned with the plane of the solar system, to have come from the spherical Oort cloud. It sits in a dynamical no man's land that existing models struggle to explain. Several explanations have been proposed. One is that Sedna was perturbed by a passing star in the early solar system, a close stellar encounter billions of years ago that stretched its orbit into its current extreme shape. Another is that the early solar system passed through a dense star cluster, where the combined gravitational influence of nearby stars could have shaped the orbits of objects in the outer solar system before the cluster dispersed. A third explanation, and the one that has generated the most attention in recent years, is that there is another planet in the outer solar system, far beyond Neptune, whose gravity is responsible for Sedna's orbit and for the peculiar orbital clustering of other extreme trans-Neptunian objects. This hypothetical planet is called Planet 9. The evidence for it is indirect, a statistical clustering in the orbital orientations of extreme trans-Neptunian objects, several of which have perihelia oriented in ways that gravitational modeling suggests could be produced by a large distant planet. The proposed Planet 9 would have a mass roughly 5 to 10 times that of Earth, an orbital period of 10 to 20,000 years, and a current distance from the Sun of perhaps 400 to 800 astronomical units, so far away that it would be extraordinarily faint, well below the detection threshold of most current sky surveys. Planet 9 has not been found. It may not exist. The orbital clustering that motivated the hypothesis is based on a relatively small sample of objects, and some analyses suggest the clustering could be a statistical artifact of observational bias rather than a genuine physical signal. The debate continues, and the surveys that could resolve it, deep, wide-field sky surveys capable of detecting a faint, slow-moving object at hundreds of astronomical units, are ongoing. But whether or not Planet 9 exists, the detached objects like Sedna reveal something important about the solar system's outer architecture. The region beyond the classical Kuiper Belt is not empty. It is not even close to empty. It contains objects on orbits so extreme that they challenge existing gravitational models. It extends outward to distances that make the Kuiper Belt feel proximate, and it grades, eventually, into the inner Oort cloud, the innermost region of the vast spherical shell of comets that represents the solar system's outermost reservoir of small bodies. The Oort cloud itself is almost entirely theoretical. No Oort cloud object has ever been directly observed in its home region. Its existence is inferred from the orbits of long-period comets, comets with orbital periods of thousands or millions of years that arrive from random directions, consistent with a spherical source population at distances of thousands to tens of thousands of astronomical units from the Sun. The Oort cloud is estimated to contain trillions of small icy bodies, extending from perhaps a few thousand to 100,000 astronomical units, nearly a quarter of the distance to the nearest star. From the inner edge of the Kuiper Belt to the outer edge of the Oort cloud, the solar system spans a distance that makes the region from the Sun to Neptune look like a small, well-lit room at the center of an enormous dark house. The belt is not the edge. It is not even close to the edge. It is merely the beginning of the outer darkness, the first region beyond the planets, the nearest part of a vast outer solar system that extends for distances so enormous that any notion of the solar system as a compact, knowable thing begins to dissolve. And somewhere in that vast outer darkness, on orbits that carry them outward for thousands of years before they return, objects drift in temperatures near absolute zero, in light so faint that the sun is barely distinguishable from the stars that surround it. They have been drifting there for billions of years. Some of them will drift there for billions more. A few of them, perturbed by a passing star, or by the slow accumulation of galactic tidal forces, or by the gravity of something we have not yet found, will eventually fall inward, toward the sun, toward the inner solar system, toward the worlds that orbit in the warmth. The outer solar system does not stop at the belt. It continues outward through the scattered disk and through the detached objects and through the inner Oort cloud and through the outer Oort cloud, fading and thinning but never completely ending until the sun's gravity becomes indistinguishable from the gravitational background of the galaxy itself. The belt is a beginning, not an ending, and what lies beyond it is not empty space. It is something older and larger and stranger than any diagram has ever managed to suggest. There is a form of danger that has no explosion at its center, no collision, no dramatic failure of systems. It is quieter than any of those things. It has been operating at the edge of the solar system for as long as the solar system has existed, and it will continue operating there long after any record of human civilization has been erased from the cosmos. It is not a force that acts suddenly or announces itself. It is simply a condition, a permanent, absolute condition that the outer solar system imposes on anything that enters it. That condition is distance. And at the distances of the Kuiper Belt, distance becomes something different from what the word usually implies. Consider what distance means for a spacecraft operating in the inner solar system. A probe orbiting Mars is tens of millions to hundreds of millions of kilometers from Earth, depending on where the two planets are in their orbits. A radio signal traveling at the speed of light, the fastest anything in the universe can move, takes between 3 and 22 minutes to cross that distance, depending on the geometry. Mission controllers on Earth can send a command and receive a response within an hour at worst. Problems can be diagnosed in near real time. Decisions can be made and implemented quickly enough to matter. The spacecraft is far away in absolute terms, but it is not isolated in any profound sense. It remains connected to the people and systems that built and operate it. The Kuiper Belt changes this in a fundamental way. At 40 astronomical units from the Sun, roughly the middle of the classical belt, a radio signal traveling at the speed of light takes approximately 5.5 hours to reach Earth. 5.5 hours, one way. A message sent from a spacecraft at that distance reaches Earth after an afternoon's wait. A response from Earth reaches the spacecraft nearly 11 hours after the original message was sent. If something goes wrong, if a system fails, if a sensor reports an anomaly, if a decision needs to be made quickly, The crew or the spacecraft is alone for 11 hours before any guidance from Earth can arrive. In many scenarios, 11 hours is not simply a delay. It is the difference between a problem that can be managed and one that cannot. A reaction control thruster that begins leaking can exhaust its propellant supply in less than 11 hours. A navigation error that goes uncorrected for 11 hours can put a spacecraft on a trajectory that requires enormous fuel expenditure to correct, or that cannot be corrected at all. A life support anomaly that is not addressed within hours can become irreversible. The communication delay at Kuiper Belt distances is not merely an inconvenience, it is a structural isolation, a physical separation from any possibility of timely outside intervention. New Horizons crossed the classical Kuiper Belt at distances ranging from roughly 33 to 50 astronomical units. The spacecraft was controlled by teams at the Johns Hopkins Applied Physics Laboratory and NASA's Jet Propulsion Laboratory. Commands were sent from Earth and took hours to arrive. Data returned from the spacecraft took hours to travel back. The mission was designed around this delay. The flyby sequence at Pluto was entirely pre-programmed, executed autonomously by the spacecraft's onboard computers because no real-time control from Earth was possible. Mission controllers watched the spacecraft disappear behind Pluto during the flyby and waited in a state of complete informational isolation for the signal to reappear on the other side and confirm that the spacecraft had survived. For a robotic spacecraft, this isolation is manageable. The spacecraft does not experience anxiety or disorientation. Its systems either function or they do not, and the consequences, while mission ending in the worst case, are not existentially significant beyond the loss of the mission and its scientific return. For a crewed spacecraft, the same isolation has a different character entirely. Human beings in the Kuiper Belt would be farther from any other human being than any person in history has ever been. The nearest other humans on Earth, or hypothetically on the Moon or Mars, would be separated from them by a communication delay measured in hours and a physical distance that no rescue mission could cross in any time frame relevant to a medical emergency or a critical system failure. The crew would be, in the most complete sense of the word, alone. The Sun, from 40 astronomical units, delivers approximately 1/1600th of the energy it delivers to Earth's surface. This is not a trivial reduction. It is the difference between a star that warms a world and a star that is merely the brightest point of light in a dark sky. Solar panels, which power most spacecraft operating in the inner solar system, become essentially useless at Kuiper Belt distances. New Horizons carried a radioisotope thermoelectric generator, a device that converts the heat from radioactive decay into electricity because solar power was not viable. By the time it reached Pluto, the generator was producing less than 200 watts of electrical power, less than 3 typical incandescent light bulbs, less than 200 watts to power all of the spacecraft's instruments, its heaters, its communication systems, its computers, its navigation systems. The power budget for a Kuiper Belt mission is extraordinarily tight, and tight power budgets impose hard choices. Every system that operates is a system that consumes power, and every watt consumed is a watt unavailable for something else. The spacecraft must be designed with ruthless efficiency, and even then, power becomes a limiting factor for the mission's capabilities. A crewed spacecraft in the Kuiper Belt would require far more power than any robotic probe to maintain habitable temperatures, to operate life support systems, to power medical equipment, to provide the lighting and computing resources that human beings need. The power requirement for a crewed belt mission is orders of magnitude larger than anything that has been designed for robotic exploration of that region. Where that power would come from? Nuclear reactors, advanced radioisotope generators, something not yet developed, is a question that has no current answer. The radiation environment in the outer solar system adds another dimension to the danger of distance. Beyond the orbit of Jupiter, the Sun's magnetic field, the heliosphere, provides less shielding against cosmic rays, the high-energy particles streaming in from sources throughout the galaxy. In the inner solar system, Earth's magnetic field and the heliosphere together reduce the cosmic ray flux to levels that human beings can survive for extended periods. In the Kuiper Belt, the heliospheric shielding is weaker, and the cosmic ray flux is correspondingly higher. Astronauts on a long-duration Kuiper Belt mission would receive radiation doses that substantially exceed anything experienced by astronauts on the International Space Station, or even by the crews of the Apollo missions. The cumulative radiation exposure over years of travel at Kuiper Belt distances would represent a significant cancer risk and could produce more immediate neurological effects. Cognitive changes, increased risk of cataracts, potential damage to the central nervous system. These are not hypothetical concerns. They are extrapolations from existing radiation biology data and from the measurements made by New Horizons radiation detectors during its journey through the outer solar system. And then there is the cold, not directly experienced by a spacecraft's crew, who would be inside a pressurized and heated habitat, but present as a constant physical reality surrounding them. The ambient temperature in the Kuiper Belt, far from any significant heat source, is close to the temperature of the cosmic microwave background radiation that fills the universe, a few degrees above absolute zero. The spacecraft's thermal management systems must work continuously to maintain habitable temperatures inside the habitat while preventing critical components from freezing in the surrounding environment. All of this, the communication delay, the power limitation, the radiation environment, the cold, the impossibility of rescue, constitutes the final and most comprehensive danger of the Kuiper Belt. Not any individual physical hazard, but the totality of what distance means at that remove from everything familiar. The danger is not concentrated in any single threat. It is distributed across every aspect of existence in that place. It is the danger of a location where the ordinary assumptions that govern human activity, that help is available, that information can be exchanged quickly, that the environment provides some basic level of support, simply do not hold. The universe at 40 astronomical units from the Sun is not hostile in any intentional sense. It is not trying to harm anything that enters it. It is simply indifferent, in the way that very large, very cold, very empty places are indifferent. The indifference is complete. The distance is absolute. And for anything that crosses into that volume of space, machine or human, the most fundamental danger is not what it might encounter, but what it has left behind. You are listening to these words from somewhere warm, somewhere the sun is a presence, a genuine warmth, a source of light strong enough to cast shadows, to grow things, to mark the hours of the day. You exist at a distance from the sun where the conditions for the kind of complexity that produces listening and wondering and drifting towards sleep are possible. That distance is not accidental. It is a narrow band in a very large solar system, and beyond it, the conditions change. The Kuiper Belt is not threatening in the way we usually mean the word. It does not scheme. It does not wait. It is simply the solar system's attic, a vast, cold, dimly lit space where the ancient material of the early solar system sits in the dark, largely unchanged, following the same slow orbits it has traced for 4 billion years. It is full of things we stored there before we existed to store anything. Icy remnants of the cloud that became the planets, debris from the collision that built our moon, flung outward and left at the edge. The danger of the attic is not malice. It is incompleteness. It is the dark corners where the inventory ends and the unknown begins. It is the things that were put there before anyone was keeping records, sitting in positions no catalog contains, following trajectories no model fully predicts. And beyond the attic, the outer solar system continues outward in a long gradual fading, the scattered disk, the detached objects, the inner Oort cloud, the outer Oort cloud, until the sun's gravity becomes indistinguishable from the gentle pull of the galaxy itself. And the solar system, as a meaningful entity, simply dissolves into the larger darkness. Somewhere in all of that space, a small spacecraft is drifting. It has been drifting for decades. It carries a golden record with sounds from a world it will never see again. Its signal reaches us as a whisper, a few watts of transmitted power, spread across the immensity of the outer solar system, arriving at Earth as something barely distinguishable from the background noise of the universe. That whisper is the thinnest possible thread connecting something we made to the place we made it. And even that thread will eventually fade as the power source dims and the signal weakens, until the spacecraft continues outward in complete silence, into a dark it will traverse for longer than civilization has existed, longer than our species has walked this world, longer than any measure of time that means anything to anyone listening tonight. The Kuiper Belt is more dangerous than it looks, not because it is full of things waiting to strike, but because it is where the familiar world ends and the indifferent one begins. And the indifferent one is very, very large.